So now we move on to chapter 19. This covers circuit theorems and AC analysis. The thing about this is you've already seen all of this in your DC course. You covered the superposition theorem, you covered Thevenin's, Norton's, and maximum power transfer in ET131. So this really is just a recap for you and an idea of how we move these into the realm of AC circuit analysis. So we're going to hit a few of the problems here just to get back up to speed. I suggest you go back. I've posted a bunch of videos for you to go back and review your DC applications on this and get your get your skills back up to speed on this. So the superposition theorem, as you learned before, we introduced in chapter 8. For use in DC circuit analysis, superposition theorem is applied to circuits now with AC sources and reactive components. The superposition theorem then stated the current in any given branch of a multiple source circuit may be found by determining the currents in that particular branch produced by each source acting alone. So just like we've seen before, we're going to turn our sources on and off. We're going to analyze the circuit based on those open circuit and short circuit applications. With all other sources replaced by internal impedances, the total current in a given branch then is the phasor sum of the individual currents in that branch. So just like we did before, it's a very methodical process. Step 1 says leave one of the voltage or current sources in the circuit, replace all others with their internal impedance. For ideal voltage sources, the internal impedance is 0. For ideal current sources, the internal impedance is infinite. Okay, so it would be a short or an open. We'll call this procedure zeroing the source. Find the current in the branch of interest produced by the one remaining source. Repeat step 1 and 2 for each of the sources in turn. When complete, you will have a number of current values equal to the number of sources in the circuit. Add the individual current values as phasor quantities. So if we take a look at this example, find the current in the resistor. Using the superposition theorem, assume the internal source impedances are 0. So we're going to replace the source VS2 with its internal impedance, 0 in this case, and find the current in the resistor due to the source number 1. So the first thing we need to do is come up with our reactances. So as we've done before, reactance for the capacitor 1, reactance for the capacitor 2, run it through the expression 1 over 2 pi FC. We get 1.59 k ohms and 723 k ohms for our reactive values. Now looking from voltage source 1, the impedance is, so now we're going to sum our impedances. So we're going to do this by using again our product over the sum relationship. So the impedance then is X sub C, capacitor number 1, plus the sum, product over the sum of R and X sub C2, then in this part of the branch, and we end up with a value then of 1.59 at an angle of minus 90 degrees added to the product over the sum. In this case, we've got polar and rectangular in the terms here. So when you convert the denominator into a polar relationship, then we can treat the numerator accordingly as we've seen before and learned before. Now we have 1.59 at an angle of minus 90 degree k ohms for X sub C1 and 588 at an angle of minus 54.1 degrees in ohms. So if you're not seeing this, if it's not apparent, you need to go back and brush up on your fundamentals of how to deal with this quotient with polar and rectangular relationships to come up with the polar value. Now, given the polar values, we can convert all of our terms here into rectangular values. How do we do that? Polar to rectangular conversion. Okay, go back to that system, and we end up with 345 ohms minus J 2.07 k ohms. You should be very versed on this now. Converting that then into a polar form yields a total impedance of 2.10 at an angle of minus 85 degrees, 85.5 degrees, and this is in k ohms. The total current then from this voltage source 1 then is V source 1 divided by the total impedance. So in this case we have polar form, so 2.10 into 10, and we change the sign of our angle. We get 4.76 at an angle of 80.5 milliamps. Use the current divider formula then. The current through the resistor due to source 1 then is given by the current divider relationship. So I current through R1 then is the current divider times the current source 1. We get a current then of 2.8 at an angle of 25.6 degrees in milliamps. So we do lots of polar to rectangular, rectangular to polar. Hopefully you've got this method down. Hopefully you figured out how to do it quickly on your calculator to solve this type of problem. Step 2 then says find the current in the resistor due to the source at Vs2 by replacing Vs1 with its internal impedance of 0. So now we've shorted Vs1, we've put Vs2 back in the relationship. We've done the same type of calculations. Okay, pull out your calculator, go through this. Calculate for the total impedance then, X sub C2 plus R X sub C1 product over the sum. We get a value then, once we do our polar to rectangular and rectangular to polar conversions, 717 ohms minus J 1174 ohms. Converting to the polar form then gives us a total impedance of 1376 at an angle of minus 58.6 degrees in ohms. The total current then for the source 2 then is, using Ohm's law, I source 2 is V source 2 divided by the total impedance. So 1376 at an angle of minus 58.6 into 8 volts gives us 5.81 at an angle of 58.6 degrees in milliamps. Use the current divider formula. The current through the resistor due to Vs2 then is given by our relationship here, I through R2. Then we get a current of 4.91 at an angle of 76.4 degrees in milliamps. Converting the two individual resistor currents to rectangular form and then add them together. So now we take our two currents that we just solved for, we have them in polar form, we're going to convert them to rectangular form, and we get a sum of 7.71 at an angle of 26.1 degrees in milliamps. So this really is a gyration and a circus of converting rectangular to polar, polar to rectangular, so that we have the right form so that we can do our solutions and adding our terms together.